Welcome, ladies and gentlemen, to our Computer Organization Architecture Specs proposal for the industrial world. We will start by introducing ourselves. My name is Nazim.
My name is Muhammad Haziq.
My name is Amirul.
My name is Hazim.
Today we present our system architecture proposal specs for our clients. The Hasbro company is a toy-selling company with branches all over the world. They have ordered multiple units of the Kawasaki RS025N 6-axis industrial robot arm for the express purpose of packaging toys from light plushies to heavy Lego blocks. With a payload carry of 25 kilograms, the 6-axis robot arm handles set items with high care precision and handling in said toys. Due to the units working in the Hasbro warehouses, our client faces a hurdle in the aspect of protection for the units. Due to the environmental hazards, the units might face problems due to extreme heat, melting the fragile equipment, metallic dust getting in the internals of the units, and the intense movements of the robot arm itself, causing the great degradation of its frame. Our mission is to design an embedded controller optimized for high durability, low thermal dissipation, and hard real-time execution. To achieve this, we reject the x86 processor and recommend a specialized ARM Cortex-R8 dual-core processor running a real-time operating system. Why ARM over x86? ARM utilizes a RISC architecture which optimizes single-cycle execution and efficient pipelining. This results in minimal high generation, allowing a completely sealed, fanless IP65 enclosure to keep out destructive dust. Furthermore, while x86 CI6 processors focus on high output via speculative and out-of-order execution, they introduce unpredictable latency or jitter. The ARM Cortex-R architecture is strictly deterministic. It guarantees that emergency stops and trajectory updates execute in exact microseconds, preventing catastrophic physical collisions.
To guarantee this determinism, we engineered a fault-tolerant multi-tier memory and storage hierarchy. For the RAM, we specified 8 GB of LPDDR4X RAM with ECC, which is error-correcting code. Factory flaw interference causes dangerous bit flips in memory. ECC detects and fixes these at the hardware level, preventing sudden system crashes. Next, we use TCM, which is tightly coupled memory. Beyond standard cache, the Cortex R8 features dedicated instruction and data TCM. This ultra-fast SRAM, which is static RAM, is mapped directly to the CPU core with zero-weight state access. We isolate critical kinematics algorithm here to completely bypass bus delays. For the last one, we use FRAM, which is for non-volatile state logs. We replace standard EEPROM with ferroelectric RAM, or FRAM, which provides near-infinite write cycles and instant data saving during sudden power losses. For storage, traditional hard disk drives are completely unacceptable. The constant vibration of a 145 kg robot arm accelerating would cause mechanical HDD heads to crash instantly. Instead, we are deploying a 256 GB industrial grade PSLC M.2 NVMe SSD, utilizing pseudo single level cell flash. It withstands temperature from 40 to 85 Celsius and heavy shocks, offering the massive write endurance needed for continuous high-speed telemetry logging.
Let's look at this, how components unify via our system architecture block diagram. The backbone of our system is the ARM M-bar XI bus matrix, a high-performance multi-master interconnect. Unlike all shared bus design, this matrix allows parallel data routing. The CPU can compute motion path while the DMA controller simultaneously streams diagnostics logs to the NVMe storage without stealing CPU cycles. The control loop operates seamlessly. Input device, high-resolution optical joint encoders stream real-time positional data over a noise-immune single-pair Ethernet bus. The CPU processes these coordinates instantly and issues immediate with pulse width modulation commands via an industrial EtherCAT port to our port output devices. The AC servo motors driving the 6 axis. This architecture directly achieves 15 watt power efficiency, complete environmental reliability, and zero latency execution.
Finally, to ensure this platform scales with your factory's digital future, our architecture includes dedicated PCIe and hardware interfaces for 3 modular upgrades. Firstly, AI Edge Vision Processing Unit. By adding a low-power neural processing unit, allows the robot to handle the real-time camera feeds for autonomous peacekeeping and defection without dragging down the main real-time processor. Secondly, 5G time-sensitive networking module. This upgrades the I/O to support wireless, low-latency factory networks for instantaneous fleet synchronization. Lastly, predictive maintenance coprocessor, a dedicated digital signal processor that can analyze motor vibration frequencies via fast Fourier transforms. It warns you of mechanical wear weeks before a physical failure occurs. By choosing this meticulously engineered architecture, you are investing in robotic control system that is ultra robust and highly intelligent tomorrow. That's all for our presentation. Thank you.
With our proposal specs for the 6-axis industrial robot arm, we hope our proposal provides help for our client Hasbro. We thank you for listening to our presentation.
Thank you very much for presenting.